Welcome to Maths with EJD. In this video, I'll be talking about linear programming forms. Now, this is necessary because in applying simplex method, we need to know that there's a form in which the problems are usually presented, but that form is usually not the best for actually solving the problems. So we have to transform into another form. And of course, when things get really big, there's another form we also have to still transform to. That is why it is important to talk about linear programming forms. Okay, so linear programming problems, linear programming LP problems, that is, can be expressed in various forms, including canonical. So one form is the canonical form, canonical, standard, and matrix forms. So we have these three forms. So understanding these forms, understanding these forms understanding these forms is essential for applying the simplex method efficiently. So if you want to apply the simplex method effectively, you need to know that you have to transform from canonical form to standard form, and even sometimes matrix form, right? So let's take the first one, which is the canonical form. Canonical form. Okay. So in the canonical form, the objective function, the objective function is presented as a maximization problem. As a maximization problem. So even if it is even if you have a minimization problem, just like I said, you have to negate it to make it into a maximization. So if you have a minimization problem, right, you can negate it to have a maximization problem because that's the standard, that's the form that is required for that's the what is needed for canonical form. So it's presented as a maximization problem, um, maximization problem, and and all constraints, all constraints are expressed, they are expressed as inequalities. So if you have inequality constraints, you should know you're talking about the canonical form, and that's the form in which problems are usually presented. Then, in addition, the non-negativity conditions, which we are used to already. Yeah, if you've been following the playlist, the non-negativity conditions are expressed, are expressed. The non-negativity conditions, rather, the non-negativity conditions are also clearly stated. Okay, clearly stated. So, a typical representation, a typical representation might look like, might look like this. So something like maximize, maximize z equals c1x1 plus c2x2 plus all that up to cn xn. That'll be your objective function, right? and all of that is subject to A11 x1 plus A12 x2 plus all of that plus A1n xn less than or equal to B1. Okay. And then you can have all kinds of constraints, right? So you can actually have A21, say A21 x1 plus A22 x2 plus all this plus A2n xn, maybe now greater than or equal to B2. And of course, that can continue till you have like N1 x1 plus N2 x2 plus all this plus ANN xn, maybe anything, maybe less than or equal to, greater than or equal to, or even equal to itself. But let's just say less than or equal to, say, of course, Bn now. So with x1, x2, all of that down to xn, all greater than 0. Talking about the non-negativity conditions. So you can see this is a less than or equal to equality. This is greater than or equal to less than or equal to inequality, greater than or equal to, less than or equal to. So this is what the canonical form basically looks like, right? This is what the canonical form basically looks like. Okay. Now, so this same canonical form, now we are going to see what it looks like in the next form. So that takes us to what we call the standard form. Standard form. So the second type of form is the standard form. Standard form. Okay. So obviously, like if you're using graphical method, right, you could just go straight from the canonical form and then start solving. But for simplex method, you need to convert the problem to the standard form. So now what I'm going to do is I'm going to you know I'm going to do the conversion to standard form based on what we have for the canonical form. So follow carefully, because now you have to turn all the less than or equal to and greater than or equal to, you have to turn them to equalities. And by doing that, you have to introduce uh, things like slack variables, surplus, and artificial variables. So in a moment, let's go. So the standard form is the specific type of canonical form. So it is still canonical form, but I mean with equalities. So it is the standard form is a specific type of canonical form where all constraints are expressed as equalities. So you cannot have inequalities here. So they are all expressed as equalities. Then this requires this requires the introduction. This requires the introduction of slack, surplus, and artificial variables. Slack, surplus, and artificial variables to convert inequalities to equalities. Okay, or better, to equations, if you like. So now I'm going to convert straight the canonical form into standard form. So let's say the the canonical form above in standard form, in standard form, in standard form becomes, okay, um, again, I mean, the maximization part remains the same, nothing changed. Oh, well, maybe it doesn't really remain the same, but it's going to be transformed like this. So maximize z equals um, C1 X1. I mean, what we have there already, right? C1 X1 plus C2 X2 plus all that up to Cn Xn. But that's not the end. Something is still going to come later. So watch out for that. But that which is to come is going to actually be determined by the kind of constraints we have. So now this is subject subject to. So the first one is a less than equal or equal to constraint. So we have A11 X1, A12 X2, and so on. So we have A11 X1 plus A12 X2 plus A1N Xn. Okay, sorry. All the jumps, all this plus A1N Xn. Now, because this is a less than or equal to constraint, right? What we are going to have to add a a slack variable. Okay, to it's more like you have A is less than or equal to B. So for you to match it up, it means you have to subtract something. So you can now maybe subtract a particular variable S so that this can be equal. Okay, so because if A is less than B, okay. Um, yeah, less than or equal to, right? So if A is less than or equal to B, sorry, you have to add something to it to match it up. Sorry. Yeah, you have to add something to A to make it equal to B because A is less than or equal to B. So like that now, it means that we have to add a slack variable here, which you call S1. And once you add that S1, then less than or equal to can then become equal to. So this will now be equal to. So this can now be equal to B1 because in standard form we need all equalities. Now that this has been added, you see that we have to also add. Okay, I guess for effect, right? I need to Control Z. Okay, this is done. Okay. Let me just leave everything the way it was. Okay. Yeah. So now we have to add something. So let me do this. So this is now plus S1. Okay. So as you add that plus S1, it also has to reflect. It will also have to reflect up here. Um, it will also have to reflect up here plus S1. Okay. And now this is equal to B1. Let me take it back. So this is all of this now will be equal to B1 instead of so the less than or equal to B1 becomes equal to B1 because you have leveled it up. So all of this was less than or equal to B1. So if you add S1 to it, which is the slack variable, then you can call it B1. Okay. Then you go ahead to the second inequality, which is actually a greater than or equal to inequality. And for you to balance it up, it means you have to subtract something from it. Okay. But I mean, in subtracting something from it, you actually do two steps. You subtract something from it and you now add an artificial variable. So you have a surplus variable and then you now add an artificial variable to it again. So let's see how that goes. So you have A21 A21 X1 plus A22 X2 plus all that plus A2N Xn. Now you have to subtract something. So let's say that will be minus S2. Then you have to now add a slack plus A1. I mean, this is a slack, this is a surplus, and this is artificial. And all of that now will be equal to your B2. Or better still, if I want to follow my perfectionistic tendencies. So I have B2. Okay. Right. So you have a slack as S1, then S2 is your surplus. So what you have to remove from the left-hand side to balance it up, then you have an artificial variable A added to it. So of course, all of that will come up here too. So now you have up here, you have plus S2 and then plus A1. Okay. Um, so that's not the end, right? We still have, of course, if you have all the other, if you had every other, other constraints showed, you do all of that, but we still have a less than or equal to going on there. So let's go down that way. So you have now a n1 x1 plus a n2 x2 plus all of this plus a n n xn. Now it's a less than or equal to, so it means you need another slack, right? So you have a slack variable S3 added so that it will be equal to Bn, right? So it is equal to Bn. Of course, this can actually be done like this. So this also goes this way, and then you have something like this if you like. I mean, that's not so necessary, but I mean, just for the fun of it. All right, so this goes. So now you have balanced it up, but of course, you also still have to add, okay, like I always do, right? This is plus, okay, this is plus S3. Let me not module that up. Let me see, plus S3. So that S3 is added to the objective function again. So this is equal to Bn. So now you have, you have turned something in the canonical form into the standard form. Basically, that's what we have here. So now, all the slack, artificial, and surplus have to now be in non-zero, non-negative constraints, right? So now, so where your exactly what we had before, right? Okay, all the x1 and all those. So where x1, x2 up to xn. In fact, this S3, right? Sorry, this S3 should actually be Sn, right? It should actually be Sn. Yes, because we are talking about the nth constraint. So that so that's Sn. So S1, x1, x2, x x up to xn, right? And then all the S1, S2 down to Sn, as well as if you have more artificial variables, like say you also have A1, A2 down to An, all of them are greater than or equal to zero. They are greater than or equal to zero. Okay, so we have all of that. We have all that. Now, that is what we have as the standard form, and this is the form in which you can solve problems. This is the form in which you can use simplex method. But sometimes it's also necessary to talk about the matrix form. So let's go for that. Uh, 3 now, we have the matrix form. Matrix form. So the matrix form is a compact representation. Compact representation of the linear programming problem that uses matrices and vectors. Uses matrices and vectors. In matrix form, the problem, the um the problem represented above, problem represented above, represented, the problem represented above can be expressed as now maximize Z equals C transpose and now I mean by this I mean very thick C transpose X. Okay, so it's still basically the same C1 X1 plus C2 X2 blah blah blah, but now it's now in matrix form. So Z is equal to C transpose X subject to AX. So now we are dealing with matrices subject to AX equals B, the right hand side. Of course, as you can see, this is an equality constraint, meaning that you are transforming the standard form directly into matrix form. So no inequalities here. So here now we have this, that A is the matrix. A is the matrix of coefficients. A is the matrix of coefficients, meaning that A is something like this: A11, A12, up to A1n, and then you have A21, A22, down to A2n, and then you have all of this down to AN1, so it's AN2, then you have ANN. Okay, so this is what A is about, where A is the matrix of coefficients, then X is the vector of variables. Where is the matrix? A is the matrix of coefficients. That X is the vector, of variables. It is the vector of variables. So meaning that X is something like this. It's X. X is the vector of variables. That is X is equal to all the X1, X2 down to Xn, together with S1, S2 down to Sn. Then if you have artificial variables also, A1, A2 down to An. So this is what X is. Then X is the vector of variables. Then C, that's C you have up here, this C here, the coefficient, that's the C is the vector of coefficients for the objective function. C is the vector of coefficients, for the objective function. Okay. So seeing how X looks like, right? And we want to end up getting C1, X1, and all the rest of that. That should be the vector of coefficient for the objective function. So that is something like C, that is C equals the coefficient now. That will be, especially if you look at the standard form. So that will be something like this. C1, C2, down to Cn. Then for all the slack variables, right? For the slack variables or something, we have 0, 0, down to 0 again. Oh, sorry. That won't be 0 now. That'll be like 1, right? So for the slack and artificial variable, that's like 1, 1, down to 1. For the surplus variables, then you have 1, 1, down to another 1 for the artificial variables, if any. Okay. But usually, right? Okay, I mean, I think it's better to indicate this. This is like for the this so these are the coefficients of decision variables, coefficients of decision variables, of decision variables. Okay. And from here down here, this will be coefficients of slack and surplus variables, while the last set, but I mean, you won't, you may not always have all this, right? You may not always have this. So then this will be coefficients of artificial variables, if you have any of artificial variables, if any. Okay, so that's C, right? We still have more things to talk about. So, and B, right? B, okay, and and B, and B, it's a matrix now. Is the vector, rather it's vector. B is the of vector of constants, and constants from the constraints. Con C is the B is the vector of constants from the constraints. From the constraints. So that means we have B to be all this now. B1, B2, down to Bn. Okay. So that's what B is. All right. So this representation is particularly useful, is particularly useful, is particularly useful for algorithmic implementations, for algorithmic implementations. Okay. As it allows for efficient manipulation, as it allows for efficient manipulation of the data involved in the optimization process. In the optimization process. Okay, so I mean, so this matrix form, right, is really useful. I'm sure the Python implementation of simplex method will definitely be based on this matrix method. So you're going to see examples of this where even for the graphical method, right, anytime you use a Python code, it follows Python. Most of the programming we do, things are better represented as matrices for easy handling, right? So that's why the matrix form is really important. So in summary, right, the simplex method is a cornerstone of linear programming that enables effective and efficient optimization, particularly in higher dimensional spaces. And then, if you understand the various forms of linear programming problems, it is crucial for leveraging the full potential of the simplex method and addressing complex optimization challenges across diverse fields. If you have not subscribed to this channel, be sure to do that right away. And don't forget to hit the notification bell so you can always get alerted each time a new video is released. And don't forget to comment. Let me know if you want me to teach a topic or solve a problem. And then like and share so that more people can have access to all of this. Till I come your way again, keep optimizing. Watch out for videos on how to set up a simplex tableau and how to actually solve simplex methods, problems using simplex methods step by step. Bye.